This is the operating system basics working with the Linux GUI. In the subtopic X Windows system, the graphical interface present in most Linux computer is based on the X Windows system, also known as X or X11. X Windows is a windowing system designed to provide a basic framework for a GUI. X includes functions for drawing and moving window on the display device and interacting with a mouse and keyboard. X works as a server which allows a remote user to use the network to connect, start a graphical application, and have the graphical window open on the remote terminal. While the application itself runs on the server, the graphical aspect of it is sent by X over the network and displayed on the remote computer. And notice that X does not specify the user interface, leaving it to the older programs, such as Windows Manager, to define all the graphical components. This abstraction allows for great flexibility and customization as graphical components such as buttons, fonts, icons, window borders, and color schemes are all defined by the user application. Because of this operation, the Linux GUI varies greatly from distribution to distribution. Examples of Windows managers are Genome and KDE, while the look and feel of Windows Manager vary, the main components are still present. The figure displays the Genome Window Manager. Okay, and this figure displays the KDE Windows Manager and the Linux GUI. Although an operating system does not require a GUI to function, the GUIs are considered more user-friendly than the CLI. The Linux GUI has a what can be easily replaced by the user as a result of the large number of Linux distributions. This model focuses on Ubuntu when covering Linux because it's a very popular and user-friendly distribution. Ubuntu Linux uses Genometry as its default GUI. The goal of Genometry is to make Ubuntu even more user-friendly. The table lists the main UI components of Unity. The figure shows the location of some of the features of the Ubuntu Genometry desktop. Menu apps, Ubuntu Dock, activities, top bar, calendar and system message, status menu. In the right side is description, in the left side is UI component. App menu. The app menu show icons for the apps that are installed on the system. A right-click menu provides shortcuts that allow starting or configuring the apps. The system search box is available from Activities view. And Ubuntu Dock. This is a dock on the left side of the screen that serves as an application launcher and switcher for app favorites. Click to launch an application, and when the application is running, click again to switch between running applications. If more than one instance of an application is running, launcher will display all instances. Right-click an application that is hosted on the launcher to see details about the application. In the top bar, this multipurpose menu bar contains a menu for the applications that currently has the focus. It displays the current time and indicates whether there are new system messages. It also provides access to the activity desktop beyond the system status menu. In the calendar and system message tray, click the day and time to see the full appointment calendar and any current system message. Access the appointments calendar from here to create a new appointments. In the activity, switch to application view to switch to or close running application. A powerful search tool is available here that will find apps, files, and values within files. Allow switching between workspace. And finish with the status menu. Allows configuration of the network laptop and other running devices. The current user can log off or change their settings. System configuration changes can be made here, and the workstation can be locked or shut down from here. And the next topic is working on a Linux host. Subtopic: installing and running applications on Linux host. Many end-users applications are complex programs written in a complex language to aid in the installation process. Linux often includes programs called package managers. A package is the term used to refer to a program and all its supporting files. By using a package manager to install a package, all the necessary files are placed in the correct file system location. Packets or package manager vary depending on Linux distribution. For example, Pacman is used by Arch Linux, while dpkg Debian package and apt advanced packaging tool are used in Debian and Ubuntu Linux distribution. The command output shows the output of a few apt-get command used in Debian distribution. Sudo apt-get update. uh, okay, reading sudo apt-get upgrade. Okay. The apt-get update command is used to get the package list from the package repository and update the local package database. The apt-get upgrade command is used to update all currently installed packages to their last versions. Subtopic: keeping the system up to date. Also known as patches. OS operating system updates are released periodically by OS companies to address any known vulnerabilities in their operating system. While companies have update schedules, the release of unscheduled updates can happen when a major vulnerability is found in the OS code. Modern operating systems will alert the user when updates are available for download and installation, but the user can check for updates at any time. The following table compares Arch Linux and Debian Ubuntu Linux distribution commands to perform package system basic operations. Task: Arch, Debian, Ubuntu. When the task, install a package by name, pacman or apt install. Remote a package by name, pacman rs apt remove. Update a local package, pacman. Okay, update and upgrade a currently installed package. A Linux GUI can also be used to manually check and install updates. In Ubuntu, for example, to install updates, you will click dash search box, type software upgrade, and then click the software updater icon as shown in the field. Process and forks. A process in a running instance of a computer program. Multitasking operating system can execute many processes at the same time. Forking is a method that the kernel uses to allow a process to create a copy of itself. Processes need a way to create new processes in a multitasking operating system. The fork operating is the only way of doing so in Linux. Forking is important for many reasons. One of them relates to process scalability. Apache, a popular web server, is a good example. By forking itself, Apache is able to serve a large number of requests with fewer system resources than a single process-based server. When a process calls a fork, the caller process becomes the parent process, with the newly created process referred to as its child. After the fork, the processes are, to some extent, independent processes. They have different process IDs, but run the same program code. The table lists the three commands that are used to manage process. Command description (PS) used to list the process running on the computer and the time it is invoked. It can be instructive to describe running processes that belong to the current user or older users. And while listing process does not require root privilege, killing or modifying older user processes does. Top used to list running process, but unlike PS, top keeps displaying running process dynamically. Press Q to exit top. And kill used to modify the behavior of a specific process. Depending on the parameters, kill will remove, restart, or pause a process. In many cases, the user will run PS or top before running kill. This is done so the user can learn the PID process ID of a process before running kill. The common output shows the output of the top command on the Linux computer. With this command, top to the day user load average task running sleeping stopping swapping CPUs swap Python 2 plus. Okay, malware on a Linux host. Linux malware includes viruses, Trojan horses, worms, and other types of malwares that can affect the operating system due to a number of design components such as file system structure, file permissions, and user accounts restrictions. Linux operating systems are generally regarded as better protected against malware, while arguably better protected. Linux is not immune to malware. Many vulnerabilities have been found and exploited in Linux. These range from several software to kernel vulnerabilities. Attackers are able to exploit those vulnerabilities and compromise the target. Because Linux is open source, fixes and patches are often made available within hours of the discovery of such problems. If a malicious program is executed, it is cause damage regardless of the platform. A common Linux attack vector is service and process. Vulnerabilities are frequently found in server and process code running on a computer connected to the network. On outdated versions of the Apache web server could contain an patched vulnerability which can be exploited by an attacker. For example, attackers often probe open ports to assess the version and nature of the server running on that port. With that knowledge, attackers can research if there are any known issues with that particular version of that particular server to support the attack. As with most vulnerabilities, keeping the computer updated and closing any unset service and ports is a good way to reduce the opportunities for attackers in a Linux computer. The common output shows an attacker using the telnet command to probe the natural and version of a web server port 80. Okay, with the telnet entering the IP address in this port, trying, connect, escape character, HTTP, bad request server, engines, date, content type, content length, connection close, HTML. This is the body of file HTML, connection close by foreign host. And the attacker has learned that the server in question is running Nginx version 1.12. Okay, Nginx, where is Nginx 1.12? The next step will be to research knowledge vulnerabilities in the Nginx 1.12 code. Only with this command you know what is the server version and the new topic Rootkit Check. A rootkit is a type of malware that is designed to increase unauthorized users' privilege or grant access to portions of the software that should not normally be allowed. Rootkits are also often used to security a backdoor to a compromised computer. The installation of a rootkit can be automated, done as part of an infection, or an attacker can manually install it after compromising a computer. A rootkit is destructive because it changes kernel code and its modulus, changing the most fundamental operations of the operating system itself, which shows a deep level of compromise. Rootkits can hide the instruction, remove any installation tracks, and even tamper with troubleshooting and diagnostic tools so that their outputs not hides the presence of the rootkit. While a few Linux vulnerability through history have allowed rootkit installation via regular user accounts, the vast majority of rootkit compromises require root or administrator access. Because the very nature of the computer is compromised, rootkit detection can be very difficult. Typically, detection methods often include booting the computer from trusted media such as diagnostic operating system live CD. The compromiser driver is mounted hand from the trusted system toolset. Trusted diagnostic tools can be launched to inspect the compromised file system. Inspection methods include behavioral based methods, signature scanning, difference scanning, and memory dump analysis. Rootkit removal can be complicated and often impossible, especially in cases where the rootkit resides in the kernel. Reinstallation of the operating system is usually the only real solution to the problem. Firmware rootkits usually require hardware replacement. Rootkit is a popular Linux-based program designed to check the computer for known rootkits. It is a shell script that uses common Linux tools such as string and grep to compare the signatures of core programs. It also looks for discrepancies and it traverses the profile system, comparing the signatures found with the outputs of PS. While helpful, keep in mind that programs to check for rootkits are not 100% readable. The command output shows the output of chk-rootkit on Ubuntu Linux. Sudo okay, rootdir checking basement beef okay, peeping commands. Although command line tools are usually designed to perform a specific, well-defined task, many commands can be combined to perform more complex tasks by a technique known as peeping. Named after its defined characters, the peep Pipping consists chaining commands together, feeding the outputs of one command into the input of another. For example, the ls command is used to display all the files and directories of a given directory. The grep command compares searches through a file or text looking for the specific string. If found, grep displays the entry's content of the folder where the string was found. The two commands ls and grep can be pipped together to filter out the outputs of ls. This is shown in the output of ls lgrephost command and the ls lgrepfile command. This is the command ls. This is a command ls with the grep file. Video, applications, rootkits, and pipping commands. Play the video to view a demonstration of installing and updating applications, checking for a rootkit, and using pipping commands. Okay, see you in the next lab configuring security features in Windows and Linux. See you in the next topic.